Hi, everybody. Welcome to AP Calculus. I am back, even though I know you saw video recording the other day. I don't know. Let me know. I mean, if you want to share how the sub day went. I mean, I think it was kind of chaotic. I know there was a switching of links, and yeah. So don't worry if you have any concerns about that day or about that Desmos, because I'm going to address it in today's agenda. So if you haven't yet, if you'd like to make a copy of today's slides, you can do so. It should be on Google Classroom. But I do want to say that we are going to go back into that same Desmos that you did when Mr. Younger was projecting my video, because I only saw like, I think about 2 folks had finished it. And when I looked at it, I feel like we still need to recover the learning goal of that day. So we're gonna go back into that Desmos today. Is my what I'd like to do to actually make sure that y'all get the credit and all of that. Juan, I don't know. I highly doubt that. I don't. Let me go ahead and open up the Power School and let's input who we have here. Oh, actually, let's first do a check-in question. So it is Thursday, everyone. It is your long day, but you got this. You could do this. Oh, yeah. Okay. Facebook, Snapchat, TikTok, or Instagram. Choose your toxin. Choose your poison. Just kidding. Which one of these is your preference? Go ahead and put that there into the chat. Okay, we got so far TikTok. We got Insta. Yes, I'm old school. Okay, I put Facebook. But I do have an Insta, so I prefer Facebook. We got Insta, we got more TikTok or Instagram. We got Instagram. So Bitmoji on the floor, Instagram. Don't know what the Bitmoji on floor. Okay, so now I'm seeing like TikTok or Instagram. So I'm guessing Snapchat is like phased out or something, because I remember that was the thing back when I first started teaching here at Envision. Everyone had a Snapchat. Isn't that crazy? Oh, you like that I'm a potato today. Okay. Yes, I forgot that I put that there. Yeah. If you could do group chats and TikTok, it would be over for Insta. So we got TikTok. 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 Okay. You know, that's how you can tell I'm not really that much on those platforms. I mean, I tried to get into it, but I mean, actually, when I first made a TikTok, it was so hard. I kept laughing, and you know, it was very. But I was getting too much into it. I noticed I would sit and look at TikToks for a whole hour, and I'm like, wait, what am I doing? And so that's why I had to actually delete the app, because I was getting too into it. So it is fun. I don't know how y'all are able to have the self control though to not let it, you know, get too into it. That is hard even for myself. Let me go ahead and put who we have. Sorry, I got really into that question. And nobody said Facebook. I mean, do y'all have a Facebook? Do you keep? I usually keep it for family though. I don't really add like, you know, random people. It's only family, people I know close to on Facebook, and so forth. And I do like Instagram because it's very informative. Like I'm learning a lot, like especially like social justice and things like that. I do appreciate that about Insta, and that's something that Facebook doesn't really have much of. So there's pros and cons. And we got, all I do is send TikToks all day. Yes, but for family, and we got no. So we have, maybe most of you don't have a Facebook. So wow, it looks like Facebook might be getting phased out. But then I heard, isn't Facebook like an Insta, like they're like part of the same thing, aren't they? Something like that, or like the same ownership, or they kind of combined. It's crazy how a few years can make a difference. Like Snapchat used to be the thing, now it's not. Okay, so this is who I'm missing, everyone. I am missing Israel, Shannon, Kaylin with a K, Evie, and Grecia. Let me know if that's accurate. I'm sorry, that's hilarious, Juan. So let me repeat that. So Israel, Shannon, Kaylin, Evie, and Grecia. That is who I'm missing here today. Oh, I never use WhatsApp. My dad, though, he does. So I don't know. I don't even know how he got into WhatsApp. Anyway, so let's go ahead and see what our agenda here is today. Agenda. So I just took attendance. The return of the Desmos is today's title. We're gonna go back into talking about the fundamental theorem of calculus part 2. There we go, the return of the Desmos. And we're just gonna continue our talk about how to actually use this theorem that was mentioned in the Desmos. Like we're gonna have some more examples and then we'll have a checkout and asynchronous number 10, what? I'm sorry, let me update this. I know I made some adjustments, so give me a sec because I know I wasn't here the other day. So I did push an assignment to be due today. Let me double check that. And hey, if you already did it, that means you don't have to worry about it. So yeah, so I pushed asynchronous number 9 to be due today, so tonight. Just so that I had more time due to the subs, I pushed that for today. So that is asynchronous 9 is due tonight. There we go. And let me know if anyone has questions, clarities, or anything like that about our stuff. Oh, sorry. I see you, Kaylin. Let me go ahead and update the attendance. All right, cool. So let's go ahead and jump into the return of the Desmos so we could all get our credit. And well, here's a little recap. So this is the goal. This is what we're trying to kind of understand. The fundamental theorem of calculus part 2. Don't worry about part 1 yet. Part 2 right now, we're going to start with the fundamental theorem of calculus part 2. The shorthand way to say that is FTC, just FTC part 2. So this is what it looks like if you were to open up a real calculus book and you were to look up this theorem. It would say this: let f be a continuous function from a to b, okay? And if capital F is any antiderivative of lowercase f defined on the same interval, a to b, so a to b, you see that right here. It's like the start and the end. That's what they mean when they say that on the x-axis. And then the definite integral is what they say of f from a to b is defined by, so they're saying how you evaluate this expression is you're going to find the antiderivative. This is capital F is antiderivative. Not only that, but you're going to be plugging in this upper limit value, subtracting, and then plugging in lower limit value. So that's what it's saying. And if you want to know how to actually read this, it's the integral from a to b of f of x dx. That is our goal. That's what we're going to try to understand here today. And we're also going to have examples. So that's our focus. It is kind of like a recap because you've seen it before, but we're going to finally kind of actually know what it's all about. So let's jump back into that student Desmos that we started on the other day. And let me give you all a minute to get back in there. And then let's go ahead and just, I'm going to see where everyone left off, what we're missing, and we're going to start from there. So kind of just re-engaging in this. So let me give you all a minute. If you just came in, we are logging into the Desmos from the other day. The code's right there. I'm updating the attendance. Welcome, welcome. Right. At this point, I'm going to go ahead and join you all now. So don't worry. I'll get the link in case you still need the code. So I have to go to my teacher, Desmos. Desmos. Okay. Teacher Desmos. And by the way, if you weren't here the day we actually first started this, you know, you have the opportunity to log in today and get some credit. So I'm going to go ahead and put the link back into the chat. Cool. So far I see Rosa is in. I see Juan is in. Sophia P is in. We have Sophia G is also in. We see Stormy is in. Kaylin with a K is in. Viviana's in. We got Shania's in. Roxana's in. Still waiting for Israel, Kaylin. We got Fernanda in. And I think okay, Edgar's now in. And if you're having any trouble getting in, let me know. So right now I turned off the pacing. Don't worry, I'm gonna turn on the pacing in a second so we could just kind of go back and what I'm noticing is, and let me just anonymize now, sorry. So I just wanted to point out who I was still missing. Awesome, I'm seeing more of these boxes light up. So I noticed that there was like a handful that probably got to those last questions, right? And then there was a few, like the majority did not, though, basically. So the majority did not get, like, for example, to slide 9 and so forth. So slide 9 and onward. So let's go, we're gonna go ahead and kind of rehash those slides. In order to rehash those, I do wanna just take us back to patterns that we noticed the other time and how that relates to what we're gonna be learning today. So let me turn on the pacing now. So I think I'm gonna take us to slide 6. All right, and let me go to, there's a few who, I don't know how this works. There's a few who are still over there on the other side, but there was a pattern when we started this investigation. So we were using geometry actually, right, to find the area under the function x. It was a triangle. From 0 to 2, first off, we got 2. From 0 to 3, we got 9/2. From 0 to 4, we got 8. And there was an actual pattern, and that pattern was 1/2 x squared. Now, that pattern is not a coincidence. That pattern is the fact that this, let me circle it. This thing right here is the antiderivative of x. So the antiderivative is giving us the pattern that's telling us the area under the curve. It's kind of wild. So from here, we see that the antiderivative is related to finding areas under curves. So that's like huge actually, because what that tells me is that we don't have to use geometry anymore. So I did see that some of you were still, using geometry, and some of you got really, really great approximations in your homework for those who did do the homework, right? But we don't have to do geometry anymore. We can now kind of use the fact that, hey, if I take the integral of something, all I need is the antiderivative. And from that antiderivative, I could get the area under a curve. So it's wild. So that is like the basic juice of the theorem that I just showed you. Let me show you the theorem again. Let me clear this. Let me know if anyone has questions. But again, we want to use the pattern. Let's move away from using the geometry, and let's use the pattern now. But hey, if you're in the AP exam, which I still have some announcements about, by the way, y'all. So I still have some announcements. I think perhaps how I'll share that announcement about the AP exam is once we're done with this, I'll go ahead and share the email that Ms. B sent me, because I think it's something worth for you to consider. So don't worry, that will come up later. But this is, again, the fundamental theorem of calculus. Capital F it represents antiderivative. So you see the antiderivative being used to evaluate an integral. And down here, basically what I did is I tried to kind of apply it to that very same example we've been doing, except I replaced the upper number with b, and I found the antiderivative right here. Then I said, okay, so then that means I need to plug in b into my antiderivative. See the b is being plugged in. Minus, there's my minus. Plug in a, I see a being plugged into this antiderivative. So cool, I'm subtracting these two. But then what is A and what is B? That's when I go ahead and substitute what's known. In this case, my A was 0. There's your 0. The upper numbers, we're just going to call that B. Well, B squared divided by 2 minus 0 squared divided by 2, basically 0 divided by anything, that's going to go away. And you're just left over with the fact that the area of x, the integral of x, is basically whatever the upper limit value is, b squared divided by 2. So that was me connecting this theorem with the patterns that we were investigating the other day. So that was kind of the whole point. Now let's say that the A and B stuff right now for you is kind of going over your head. Like, I don't know. Let's actually do some examples. That's where the examples help us. So I'm going to go ahead and clear my screen. And if the variables make sense to you, that is awesome. But let's actually do some. I know a lot of students, I mean, back when I first taught AP Calc, from my beginning years of teaching it, all the time they'll be like, well, every time you show us, like, it looks really complicated, or when you show us the theorem, it's like, looks like crazy, like, you know, the rules and stuff, but then when we actually do the examples, it makes sense. So that's the part we want to focus on, how to apply the theorem. And here was an example. So of course, if you look at this picture, I mean, if you look at this integral, so the integral from 1 to 3 of x dx, and I went ahead and I included the picture of the function y equals x. Now, of course, you can go in and use geometry, like, sure, you could totally do that, but when it comes to like curvy graphs, you actually cannot use geometry. That's going to be too much work for you to actually use geometry. And in addition, you'll only get an approximation and not the exact area. In this case, yeah, you can. It's a trapezoid, so you could get the perfect area. But I'm going to actually, instead of finding the area of this trapezoid, I'm going to be using the theorem, the shortcut. So this is basically the shortcut. So this is how we do the shortcut. Step 1, find the antiderivative of this. The antiderivative has the notation capital F. So how do I find the antiderivative? Let me remind you all. The antiderivative, how you find it, is basically this rule. X to the n plus 1 divided by n plus 1. Because this is just x, there's an imaginary 1. So you have x to the 1 plus 1. That's what gave me my 2 right here. And then you have divided by 1 plus 1. That's divided by 2. Well, that's the same thing as bringing this 1/2 to the front. So step 1, find your antiderivative of your function. Step 2, you're going to plug in the lower value. Oh, sorry. It starts off with plugging in the upper value first. Don't plug in the lower value first. So you got to plug in the upper value first into your antiderivative function. So notice how it's the same as this, except I plugged in 3. Then I'm going to subtract, and then I'm going to plug in the lower limit value. So it's always top minus bottom, basically, into my antiderivative formula function. That's me doing this part of the fundamental theorem. So notice that. Then what comes after that, y'all, is just simplification. So using some algebra, remembering PEMDAS, you would get 9/2 minus 1/2, which basically is 8/2. Well, hey, 8/2 is equal to 4. So the area of this trapezoid, everyone, is 4. And I did that without using geometry. I did that with antiderivatives. That is the key here. We did it with antiderivatives, and we're going to be doing it with antiderivatives because we're going to take up too much time if we try to do it with geometry. Let's see, does anyone have questions about this before we jump into you guys going in and trying it?
Yeah, I had a question.
Yes.
So the FB minus FA, can you repeat what that was again?
Yes. And this, okay, great. Yes. So this FB minus F of A, so capital F represents antiderivative. And then when it says F of B, that is telling me that I need to plug in this B. So this is A and this is B. My B in this case is 3. So notice how I basically plugged in my B, my 3 right here, into my antiderivative. So
Oh, okay.
yeah, and then the minus part, and then there's the F of A, so you're just plugging in that lower number at 1 into the antiderivative.
Okay, that makes sense.
Awesome. Yeah, great question. Let's see, are there any other questions coming up for us? You could unmute, or you could also, if you want to send a private message in the chat as well, whatever works for you all. So I'll pause here to see if any more questions are coming up for us. If not, we could jump into examples. Okay, cool. And if questions come up, feel free to, ask me. I'm happy to help out. Let me clear up my drawing. So yeah, I know it's like the sub video that was so last minute. So of course it's like I definitely was anticipating coming back to this. So I'm gonna go ahead and move us. And I see 8 folks with us. If you're missing, I definitely want you to get your credit to move us along. But this is what I saw the other day. So let me go to the student view first. So first off, you're asked to find the integral. And I asked, show your steps. So I meant show your steps. And then I wanted you to sketch what the corresponding area would look like in your graph. Now let's take a look at what some of you had done. And 1, 2, 3, 4. 4 students had done this. So I'm going to give opportunity. I really like, so either Herman's looks great. I mean, this one also, I like the fact that they're imagining it's like the Desmos where you're using those lines. Awesome. And it looks like they were calculating, they were trying to kind of calculate this using geometry, right? This particular student. Then we have Pierre. I mean, I love it. So it's correctly shading the correct area, which is awesome. So we know how to shade what area this is representing. So that's cool. But let me look at the work. So take a look. So Gregory here, right, did it with geometry. So actually what I'm asking you or I'm pushing you to do is to try to use antiderivative to prove that area. So Gregory got 10, right? So Gregory got 10 for the area. But I actually see another Sophie Pickard, right here. They used the antiderivative. Notice that. They plugged in the upper limit value, which was 5, right? And then they minus and they plugged in the lower limit value. They went ahead and simplified and they got 12. So this is a correct application of the fundamental theorem of calculus. You're using antiderivatives. So I see Pierre de Fermat right here also used the antiderivative method. And Fan Chung down here started to use that. I think there was a conversion of decimals. Whatever helps. If you want to keep it as decimals, go ahead. Try and see if you also get 12, because I do see 12 coming up. So I wonder why Gregory got 10. So let me go ahead and give you all some time to finish up your sketch. And then I'll go over how I would use the fundamental theorem the way those students were doing down there. So for those of you who are still a little bit lost, I wanted to make sure I re-explain how to use the antiderivative to find the area instead of you trying to figure it out. Oh, I know, Gregory. So Gregory, what mistake you made is that you assumed this was a triangle, but if you actually look, this is a trapezoid. So I see that you use the triangle formula, 1/2 base times height, but this is for a triangle and that is a trapezoid. So you want to break this, if you were to do geometry, you would break this into a triangle and a rectangle and then you could find your area. And then you should perhaps get the 12 that everyone else is getting. And that's for Gregory feedback there. All right, so I'm gonna give us a few more moments to get our sketches in and to go ahead and try to apply fundamental theorem part 2. So use the antiderivative. And I'll be back to try this out.
Hi, I had a question.
Yeah, go ahead.
So I see the graphs, but I see that some of them start at 1 and some of them start at 0. Which one's right?
That is a good question. So how to tell which is which? I mean, well, first off, let me see if anyone knows that. So start at 0, because I see what you're saying. I see like this here, Dana's graph is shading and it looks like a full triangle, correct? And then we see Herman's graph starts at 1, goes to 5. This one starts at 0, goes to 5. Which one is right?
Mm-hmm.
Question. So first, let me see if anyone knows who is correct. So we have Dana or Hernan. And can you explain why? Okay, so Edgar says Dana. Can you explain either by typing it or unmuting why is, sorry, you said Dana is right or wrong? My bad. Okay, so Edgar says Dana is right. Can you explain to us why you think Dana is right? Either by typing or anything. And anyone else is open to, you could jump in. So Dana's graph looks like this, by the way, y'all. Okay, so I have a private chat. The integral goes from 1 to 5. It says because the bottom number is 1, so it starts at 1 and ends at 5. Okay, so Edgar, I see what you're saying, but does Dana start at 1? If you look here at the shading, does that start at 1 or 0 though? Is Dana right or wrong? Oh, okay. So Edgar, you're saying, so then we're saying that this graph is shaded incorrectly because you were saying the bottom number is 1. That tells us to start at 1 and the upper number is 5. And I also got a private message that says the integral goes from 1 to 5. So to answer your question, Roxana, so it should start at 1. So my feedback would be for Dana, you want to shade this way and then just, scratch off the parts before that. So it starts at 1 because the lower limit starts at 1 down here. I just call that the lower limit number. There we go. So that is an amazingly great question. Thank you for asking it. And hopefully it made sense. If it didn't, y'all feel free to, continue to ask. And that's correct. So it is not a triangle. It's going to look like a trapezoid. Sorry, is that what it is? Trapezoid, right? Let me clear and show you. Your graph, your shading should look like this. Either like, this one's a good, see it starts at 1, goes to 5. This is not a triangle because it has this little part right here. So this is a trapezoid. Oh, okay. Can't tell the shape. I think that's a trapezoid. Yeah, they look like this. Let me just trapezoid. Yeah. They have 2 parallel sides and then, yeah. So I think that is the trapezoid, the 2 parallel sides with this one and this one. So yeah, it should look something like this and it should not be shaded before 1. Yay, I see Dana there adjusted the graph. We are getting more jumping in there. So again, please make sure you try this out so you could get your credit today. I should see dots, showing that you're attempting this, that we're learning, and that we're trying to apply this. Okay, so then down here, John von Neumann is doing the geometry method. And with the geometry method, proving that the area is 12. And notice how there's other students using the fundamental theorem and they're also getting 12. So it's like it proves that this theorem is working for us. And then I see Dana setting that up. Awesome. So let's have a few more minutes on this, but 1, 2, 3, 4, 5, 6, 7, 8. So 8, I see 8. I don't know who we're missing here, y'all. But make sure you include your little sketch here with your contribution. Okay, so I don't see any more sketches being added or any more responses like changing down here. Usually I see, oh wait, I do. I do see James Sylvester is still typing out. So James Sylvester, it appears like they're doing the area method. Awesome. So I'm gonna go ahead and soon transition us to the next slide, everyone. And in this next slide, you're gonna find something interesting, right? So let's see for those geometry errors, if you could apply your geometry here, or if you wanna use the fundamental theorem. So I'm gonna take us over. So as long as you started on typing out something, don't worry, you'll get your credits if you're concerned about that. I'm gonna move us over and I'll be following up with those who I'm missing responses. Again, super important. I wanna see that y'all are learning and trying this. But here we go, y'all. So let's say I have the integral from -1 to +2, and now my new function is 5x squared dx. So notice how 5x squared looks like, it's not looks like, it is a parabola. And I am seeing that many of you are shading the correct area. So it starts at -1, ends at 2. Well, this one added 2 lines, but they're not, fully shading the area. Let me see if, let's see, Herman there kind of outlined in orange what that area looks like, kind of. So go ahead and first shade the area, the correct area into the curve. So we want to first verify, do you know visually what we're asking you to do? Like visually, what is the area that you're being asked to find when you're doing this integral? So first do that, and then we'll take a look at some of the responses and what we got. And then y'all, let me go ahead and just stop my share for one moment, okay? So I'm gonna stop my share, but continue on this slide. You're still on slide number 10, and I wanna see what y'all think. Give me a second, I'm gonna stop my share because I wanna just see who we're missing. I wanna prompt them in the private chat, okay, everyone? All right, everyone, welcome back. Welcome back. So, and if you saw a private message from me, it's more so because, you know, I definitely just want to see where you're at and how I could support you. But let's go ahead and check this out and what we have. So, although it's like, you know, this would look like something I do in high school. So even though it's like like that, that is the correct shaded area. So thank you, Pierre de Fermat. You shaded your area. So our goal is to find the area of that. But our goal is going to be that because this wave, I'm sorry, this parabola is curvy. It is curvy. That means it does not have sharp corners. We cannot use geometry. Like, yeah, you could use Riemann sums, but that's going to give you an estimate. We're going to have to use the fundamental theorem here. So we're gonna have to, because these are not two triangles, y'all. This is like that would be a curvy hypotenuse, and that's hard to take into account. Now, you can use geometry to approximate, like, yes, like perhaps let's say in the AP exam it's multiple choice and you try to approximate, you could kind of get close to the answer. But our goal here, our learning goal is we wanna connect areas under curve with antiderivative. There is a deep connection with that. So let's go ahead and see what we have here. So I see 5x squared, and I see that we're plugging in the upper limit value. See, I see 2 being plugged in, subtract, and I see the same expression, but we're plugging in the lower value. However, I see, it looks like Doris here has a different antiderivative that they're plugging into. So I see a 4. And I see that they're plugging in the lower limit and subtracting the upper limit. So remember, for Doris feedback, you actually want to plug in the top number first and then subtract by the lower number. So no, top first. Top always goes first. So you want to just adjust that. Yeah, because then you're getting a negative area, and thus, you know, the area would be positive for this one. All right, so let's go ahead and see. Then we have Pierre de Fermat using 1/2. They're plugging in the upper and they're plugging in the lower. So I'm seeing the 1/2 x squared come up from the prior slides, right? That formula. Mary Jackson, however, I see the third power coming up. So Doris and Mary, they're getting this third power, and I'm wondering about that. Like, I see some of you have the third power. I see some of you have the second power. Let's talk about that. So let's talk about that. So to apply the fundamental theorem, oh, let me see the chat. Let's do this. Okay, step 1, y'all. I'm doing fundamental theorem. So step 1, I know usually it's great to have the formula right next to me, but step 1, find the antiderivative. So I'm going to bring this down. Now I'm going to remember the antiderivative formula. It's x to the n plus 1 divided by n plus 1. Okay, cool. The 5 is just going to be right in the front. So cool, there's your 5. Now this 2 is going to be added. You're going to add 1 to it. So it's going to be x to the 3rd. And at the bottom, you're going to have divided by 3. So you could write it like this, or you could have wrote it like this. So 5/3 x to the 3rd, whatever is nicer for you. Step 1, antiderivative. Do y'all see how I found the antiderivative? Notice how I just kept the 5 in the front. I just kept it there, but I focused on taking the antiderivative of the variable. That's what I did. So step 1, antiderivative. So that is where some students were getting that third power that we saw. That is where we're getting that third power. Now I didn't check to see the rest of it, but let's see if anyone has questions about what I just did in step 1. Step 1, find the antiderivative. You have this one or you have this one. I think I'm going to use the second one. I don't really like the giant fraction. If you like giant fraction, that's okay. And then it says, I just noticed I did it wrong. I know we have to find like the derivative. Yeah, thanks, Rosa. So the opposite of the derivative, so antiderivative, that's correct, Rosa. So that is what we're gonna do. Now, I'm going to go ahead and let me just erase this because I don't like this one. And I'm just gonna use this. Actually, I'm gonna rewrite it. So I'm gonna rewrite it as 5/3 x to the third. And that is my antiderivative. And I'm just gonna delete the rule. Oops. Okay, so step 1, antiderivative. Step 2, let me type out step 2, so I have it right here. That's when you're gonna, so capital F, y'all, represents antiderivative. That's when you plug in the upper value, so B, minus the lower value, capital F, which is A. And we're plugging in the lower and upper into the antiderivative. That's what this is telling us to do. That's what it represents, because capital F means antiderivative. So we're going to plug in first 2. So we're going to say, okay, 5/3, plug in 2 to the third power, minus, now we're going to plug in -1 into my antiderivative. 5/3, and we have -1, and then it's to the third. So that is, I know my steps are crooked, but here's my antiderivative. Here's my second step where I'm plugging in the upper value, subtracting, plugging the lower to the antiderivative. Now, if I do this math, it should be that it's going to give me the exact area under this curve that y'all shaded here. It should be, according to the math, according to the calculus. So all we got to do now is kind of simplify this with some algebra. So 2 to the third power, that is 8. Right? 2 to the third power is no. Yeah, 2 times 2 is 4, and so that's 8. 8 times 5 is 40. Then we got divided by 3. Let me know if anyone has questions. So I did, this is 8, 2 to the third is 8, times 5, I got 40, and then I brought down the divided by 3. Then we have -3 to the third power. So that's just -1 times -1, that's +1, times -1, that's again -1. So then that's going to be minus 5/3 times -1. Basically, these two negatives right here is going to turn positive. So it's going to give us 40/3 plus 5/3. Sorry, y'all, I can't right below this for some reason. Not for some reason, it's so it's going to be a plus because of the double negative. And that's going to give me 45/3. Now, by the way, you could actually convert all this to decimals if you'd like. What is 45 divided by 3? So actually, oh, what's in the chat? 15, really? Well, that's a very nice area. Oh, and why did you put 3 in the denominator? Is it because of the exponents? Like down here, this denominator? Like the initial time I found the antiderivative? Like, why is this 3 down here? Or why did I put 3 down here? So this was, let me call this A, and let me call this B. So there was a question about why did I put 3? And is it because of the exponents? So do you mean this part A or this part B? Like the initial time I put divided by 3 or the second time you're seeing it happen down in the last steps? Let me know and then I could address it. And so Juan says we got 15. Wow, that's really nice. It's a nice area. Yeah, sorry for the messiness. And but I could already start telling why we got 3 here. I mean, if you want to know. So usually when it comes to the antiderivative, the rule is this. And let me write down the rule. I'll write it in blue over here. The rule is you do x to the n plus 1. So because this was a 2 right here, because this was a 2. So this is the rule. Sorry, let me finish writing down the rule. And because this is a 2, that's going to give me x to the 2 plus 1 divided by 2 plus 1. So usually what you're seeing is that it does, if that's what you were asking, it matches with the exponent. The denominator number is matching with the exponent when you're taking the antiderivative. And that's why we have a 3 here and then a 3 down there. So it became 3 when we used the antiderivative rule. Let me know if that helped. If not, I am happy to re-clarify. So our answer is 15, everyone. Can I see that we are making an adjustment in our work to see that if we understand that we should be getting an area 15. So the area under what we just shaded is 15. It's nice how it's a nice clean number despite the curves. Okay, so I see Sophie Pickard got 15. Doris did not get 15. So it looks like what Doris needs to do, I think the only difference was that I had it divided by 3 or something in the initial round, I think. And then the 4 needs to turn to a 5. Okay, awesome. Okay, and then for Pierre de Fermat used the old antiderivative formula that was for the prior function. So because we have a new function, you had to find a new antiderivative. So you want to just adjust that formula. So I don't know if this person is actually here today. All right, Vaughn Newman, awesome. All right, Dana, and then we have Mary. So we have those who are participating here. So I don't know if Pierre was from last time, y'all. But yay, okay, good. So we're getting some adjustments in our answers. Let me know if anyone needs more time on this portion so you could, give it a try. Yay, okay, cool. So I'm hoping that clears up a little bit of the misconceptions that some of you might have had the first time you've seen this. Yes, wait, let me see. There was a question about the Mary Jackson's. Yes, Mary Jackson's does make sense. Mary Jackson converted to decimals, but you see how even if you did convert to decimals, you still get 15. So if you want to convert to decimals, y'all, you could do that. I just wanted to show you all for, I guess I usually like to work with fractions, but if you want to convert to decimals, you are free to. You could still get the same answer. Okay, y'all. So I hope that did clear the air with some of what is the fundamental theorem of calculus. And we're going to use antiderivatives to make life easier and calculate areas under curve. It's going to be coming up for our, next mini final. So stay tuned for that. But again, as you know, I'll always be here to support and to help in any way I can meet you all. So I'm going to take us to the very last slide. Some of you actually feel free to adjust this because you initially gave yourself a rating, right? So feel free to adjust this if it's different now, right? So go ahead and rate your understanding of the fundamental theorem of calculus part 2. That's what we're just doing right now with the antiderivative. 1 being not so well, 10 being you understand it very well. Go ahead and take your time on your rating. All right, y'all. So I'm going to go ahead and bring us back. I really appreciate these honest reflections. So again, we just like the fact that y'all there was a sub the other day, so it was very hard for you to kind of like get to dig into the meaning of this without the opportunity to ask questions because I wasn't there. So we just encountered this basically. So you just had some exposure to this, and so it makes sense that you're gonna have many questions, and you still need more practice. Like we only had like two, right? I did prepare some more to go over, but due to our timing today, of course, we're going to have to just continue to talk about this next week. But if you are curious, right, like if you need some more practice, I did have, like, I had a Google form, but we could do that next time. Right here, sorry, slide number 6 on today's slide. I provide some more examples. So for those of you who are talking about like why the fractions are coming about and so forth, if you want to see some more examples, but these are so on slide 6 and slide 7, if you're curious. But we could also go ahead and talk about it Monday so that we, understand a little bit more on how to do this. So I appreciate the honesty. I love the mention of the chores because I know what you mean. Yeah. And I also like this, how that last one really tripped people up. They didn't really understand the fraction part, the fact that the graph is curvy, and then that n+1 part getting tricky. So I appreciate that. 5 to 6, I think that's pretty, I think it's pretty awesome. And I also think that you self-reflecting on your learning is actually super beneficial right now. So yeah, so I'm gonna go ahead and stop my pacing so that way you could go back if you did not complete a portion but y'all are still anonymized. Just make sure that, when I go back to the parts that should have responses, that it has a dot, So I just go through and be like, okay, did they try it? Awesome. Not okay. But yeah, so I always give you opportunity if you'd like to, remake something. Okay, y'all. So thank you so much for your reflection. We are at 10:55. You have your next class, so I'm gonna go ahead and let you go. Bye, everyone. Awesome. I love this today. Bye. Have a great day. And yeah, totally. I'll stay right here if you need to talk with me. Yes. And then hey, Jay.
Hi, Mr. Dono. So, I believe the other day, last week on Thursday,
Uh-huh.
I was not in your class,
Uh-huh.
and then for a sub, I wasn't also.
Uh-huh.
However, so I did understand for the and the things that we were doing, the worksheet that you did on asynchronous, I think 7, that was due on Sunday or Monday.
Right.
So number 4 was the one that I kind of got confused, and I never got a chance to ask you how to do it because my answer was 16.9. But the other 3, I learned from a video on YouTube on how to do it, and I understood on their way how to do it. With the decimals part, that's how I did them. No, you said to do them under a graph, but I just did them with a decimal. But for the 4th one, I didn't understand how to do it.
We're talking about semicircle. And do you have a class right now, by the way, just to know?
No, I have portfolio.
Okay, cool. So I could totally pull that up. So let's see, async number 7. And did you turn it in or oh yeah, you did. Oh, actually, no, I don't see it. Are you able to share me? Wait, I'm confused. Asynchronous.
It's the one with the 4 asynchronous lesson number 8.
Oh, okay, 8, my bad. I was like, I think 7 was a Google form. Okay, so let's see. Okay, I see it. And for the last one, the answer was supposed to be. Do you remember what they said was the answer?
Oh.
What we're supposed to get for this one? Oh, you were trying to do it anti-derivative way here?
Mm-hmm. So
Yeah.
if you check the other first 3, I got the same answers. I got the correct answers for all of them.
Oh, and this is you doing anti-derivatives, right? Like the thing I was talking about today.
Yeah.
That's awesome. So for this one though, if you want to find the antiderivative of that is actually more difficult. You would need something called chain rule. So an additional rule to actually find the antiderivative of this thing. And let me go ahead and see what was the answer for that last one. So for that one, It is perfectly fine to use geometry. Yeah, so there's something called chain rule for integral if you want to do this problem. It involves like you substituting. Do you want to talk about that or you want me to show you how using geometry?
Give me a sec, Marcelo. Give me a sec.
Okay.
Uh, so what did you say?
Oh, my bad. So in order to do number 4 using the antiderivative way, you would
Mhm.
actually need some additional rule called chain rule. So
Mhm.
I was curious if you want me to show you the chain rule method, we could do that. It would probably take like 20 minutes to explain why it works. Or you want me to show you how we would use geometry to figure out number 4.
Whichever one is fine. I mean, I have no class. I don't know if you have a class.
No, I think I don't. No, it's a 5th period, right? No, I don't. So I'm okay right now. So let me show you the geometry way. So I would go to desmos.com and I would just first off plug in this, whatever this is.
Mhm.
So were you said you weren't here this day when I went over this one?
No.
Okay. So yeah, so if you're able to find the area of something with geometry, like you're totally, that is fine. But sometimes, when something's curvy, you're gonna have to do the antiderivative. So it's minus x squared.
It's 36 minus x squared. Yep.
Awesome. So as you can see, when I graphed it, it looks like a semicircle. So basically what we need to do is find the area of that semicircle. Once we have that, graphed. So basically if I'm to shade, oops, this whole region right here, from -6 to 6, is what it said.
Mhm.
So would you know how to find the area of the semicircle?
Do you have to find the area of like the triangle, like the right triangles, or
You see right triangles in here?
no?
I see a
uh,
full semicircle. Right.
a circle, but that would be like with um pi and stuff.
That's true. And if I look back at the answer, right? Like as you got answer.
18 pi.
So what is do you know what the area of a circle is?
Pi times radius squared.
Yeah. And that's for a full circle, right?
Mhm.
So if I want a semicircle, what do I do with this formula?
Pi times radius squared divided by 2.
Perfect. So that formula is going to give me the area of this semicircle. Well,
I see.
what is the radius?
12.
So
Oh
12.
no. 6. Sorry, 12 is the
Right.
diameter.
There we go. Yeah. So this is going to be equal to pi 6 squared divided by 2. What do you get when you do that?
Don't you just
You could simplify like the numbers, like what 6 squared is.
okay. Let me see. 6 and 6, 36. So it's 36 pi divided by 2.
Yeah. Could we simplify this further?
Uh, to 18 pi. Oh, and then that's the answer. Wow.
Yeah. With geometry would be easier. There's something
Uh-huh.
called U sub, but we didn't get a chance to like fully cover that. And I
Uh-huh.
will. Oh no, I didn't give you all the guys the announcements about the AP exam, and I think you wanted to know it.
So what is it with the AP exam? What would like
So
happen?
basically, Miss B, I asked it in an email. So last year, what had happened is that the AP exam was in May, right? And we went ahead and I looked into the dates, and they said there are paper exams in May, but the only
Mhm.
one that's online is actually June 9th. And that's after.
Your graduation.
That's right. So basically, what I wanted to share, what Miss B said, is that if seniors are thinking like, whoa, that's way too late after the year and I don't want to take it, there's gonna be no consequence. So as in like you won't be required to if you feel like,
Mm.
but if you really want to take it June 9th, it's fully paid for and it will be online. So it'd be up to you guys.
And if it's in paper, do we just go to the school?
No, so that's the thing I asked, like, are y'all gonna have an in paper one? And she said no. So
Because I know for Spanish, we're gonna have one at school for AP
yeah,
Spanish.
I asked about that. She mentioned something about the reasoning for Spanish being paper and not at home. I don't remember what exactly was the reasoning, but at the current moment, they did not order any paper exams for AP Calc for May. So they're
Mhm.
only having June 9.
June
Just
9th is a Friday, right?
let's see. Yeah, so
Because
ooh,
if it's
I forgot to share that though. I
because
wonder.
if it's a Friday, I'll just go ahead and do it.
Or I think I'll just share it Monday. That way
Oh,
I'll,
it's a Wednesday.
it's a Wednesday, okay. And then the June 4th is a Friday graduation, right?
Yeah.
Yeah, so I'll leave it up to you all if there's not gonna usually it was that you were required to take it, but because of this,
Oh, but it's online, right? So then we were just go join our class and stuff.
yeah, there's like the instructions. I would send you all the instructions. You still have your email and stuff. So if you're interested, just let me know. So I guess I'll have to tell everyone on Monday. So I'll make sure I make a slide and everything to go over this.
Okay.
Because it's all the way until June 9 now. So yeah.
So the only asynchronous work we have is just asynchronous 9, right?
Right now, yes. Because I had a
Okay.
sub, so I just decided to push that back to today.
Okay, thank you. Then I'll see you Monday, Mr. Donna.
Yay. Thank you. Oh, by the way, my I started watching that one show you recommended. Oh, I forgot the Jenny Rivera one.
Oh, yes.
It was really good. My sisters are into it. I think we're like midway, and I haven't had time recently. So,
I know the episodes are really long and there's like 100 something.
oh, I don't like when they keep changing the characters, even though I understand, like they're getting older. But
I know.
I miss the I miss the first character. But yeah.
Yeah, I did too. She resembled a lot of her, or like the way she spoke.
That's very true.
Yeah.
Awesome. But okay, I'll let you go so you
Okay.
can take a break. Thank you so much for staying.
Thank you. Bye.
Bye.